When a bug takes off, it's an amazing coordination of agility and power. As they fly through the air, they can perform loops, pirouettes, or even move backwards. These maneuvers inspire scientists seeking to design robots that can move with similar ease and speed. But it's not easy to move a camera fast enough to record an insect in detail as it flits from place to place. Now, researchers have come up with a new way to continuously capture all the nuanced movements of insects in flight.
For completely understand the insect flight, we need more advanced system to not only follow the insect, but also zoom into the insect to have more detail of the insect locomotion. Traditionally, we use a fixed motion capture system. We kind of lose a lot of detail of the wing when it moves, or even the body of the insect. People have the ability to record high detail motion of the insect, but we record the insect behavior in tether condition, where we fix the insect in a fixed position. Working with tether condition is very different from the freely behavior animal. For example, we want to see how the wing changes in freely flying condition, and how the head angles.
So Deng and his team set out to develop a recording system that allows the insect to move freely.
For our tracking system, we call it BYO, like bring your own camera. You just bring the system in the field and then plug the camera in. We have the mirror that's driven by the two motors. One is pan. For the pan axis, they can rotate like 360 degrees. For the tilt axis, because we know that there's an optical path, so it can only move around like 60 degrees. We have combined motorized mirrors and camera for recording position of insects, and with the information from a reflective marker on the insect.
To test their tracking system in the lab, they followed a drone instead of an insect.
When we use reflective marker, we can increase the signal to noise ratios. It's a very popular method for motion tracking industry. In our system, we have an illumination, infrared light. It will beam the light into that marker, and then the reflected light will go back to the system and go to the camera. The information from the tracking camera is used for the control system to drive the mirror. It's a real-time processing. Whenever the marker moves out of the center, the system now realizes that and direct the mirror immediately to move it back. We try to reduce the motion blur when the insect moves, because insect move quite fast, right? We have a system that can move up to like millisecond in latency.
When they took their tracking system into the real world, they observed two insects, locusts and bees.
It's very hard to look through the gliding phase in detail, because we cannot predict how or where the locust jump, right? But with our system, we can track from the beginning to the end of the jump. And some of the locusts perform quite nice behavior like mid-air acrobatic, where they can change the orientation of the fly by changing their legs or their wings, or glide and then land. We observe the bees from landing from flower to flower. We can also see how the leg move and abdomen move, as well as how the wing flap throughout the navigation. Information is very important when we look into like insect decline, and we want to see whether certain pesticides affect the bees' behavior.
Threats like pesticides and climate change can impact the nectar and pollen available to bees. Putting transponders on insects and tracking their movements can show the routes insects travel to food sources. Deng and his team simplified their tracking system to fit onto a drone in order to follow a bee's flight path. Equipped with a different camera, this could reveal subtle behavioral changes along these foraging routes, like whether the insects steer their wings differently.
We actually use the same concept or same idea with the system that we mount on the drone. So the camera now driven by two motors, and the task of the drone pilot now is try to steer the drone to a good position so that it have the system, and also try to follow the insect as good as possible. In our demonstration, we can follow the bees up to 100 meters, but we can easily extend it beyond that. But of course, to more practical application, we should aim for autonomous system so that we can chase the animal without the pilot, for example. Currently, we use reflective marker, but it's possible that we can remove that, because we can use some deep learning model to kind of track the insect. It will reduce the complexity of the system and also the setup.
Deng already has his sights set on other insects to observe, which may inspire new robots.
My kind of favorite insect is the beetles. I work with beetles for years, and I really like how they fly. We kind of understand the role of the individual muscle, but we don't know how the beetle combine them to perform complicated tasks. For example, how they perform like hovering. We want to have the system combined with other technology that we develop, like for example, wireless backpack for investigating like the muscle activation or induced muscle contraction to understand how insects really use those muscles in flight.
As more researchers build this tracking system, they might unlock insect maneuvers we've never seen before.